Okay, so hi, let me start with some short introduction. My name is Dian. I'm currently a software developer at Acronis. I'm mostly working with Golang, Elasticsearch, and a little bit of Python every now and then. Allow me to introduce briefly about Acronis. So Acronis is a leader in cyber protection. It is founded in 2003 in Singapore, and currently it has a dual headquarters both in Switzerland and also Singapore. In Singapore itself, Acronis has one of its biggest R&D centers, and it employs more than 1,600 employees globally across more than 30 locations. It provides cyber protection features, including platform and a set of protection services on top of it. If you're interested to know more about Acronis, feel free to visit our website and you'll be able to find out more about it. But one thing for sure that I want to share with you is we love Golang and we are building a lot of exciting stuff with Golang. And that is part of the reasons why I'm here today to share a little bit about Golang with all of you. All right, so without further ado, let's start with the talk itself. So I'm going to share roughly 5 topics, and I kind of give some hints and short title for each of them so you kind of get intrigued about each of them. So let's start with the first one. So as the title suggests, it is a question on whether the program will halt or will it stop when we run it. So let me briefly explain what the program is doing here. We have a test function here. It's just initializing an integer called a, and then within a loop, it does some computation. So you can think of it as just a simulation of some computation function, right? And in the main function itself, we start by setting the go max procs to 1. And after that, we print a start string, and then we spawn a go routine. The go routine is doing nothing, but keeps on looping in a tight loop, calling the test function again and again. So it is simulating a heavy computation. After that, the main program will sleep for 100 milliseconds, and then it will print done string. So the question will be, if we run this program, will it stop or will it keep on running? Yeah, unfortunately, it'd be nice if you can leave some comments, or yeah, I'll give you some time to think about it. Even if you don't want to leave comments, it's fine, but just try to guess or think like whether you think the program will halt or it will keep on running. Yeah, maybe I kind of give the answer away by putting a GitHub issue here. There's an issue, so it should be an issue. But the answer to the question is, it depends. The answer to this question is, it depends on your Golang version. For example, if I run this, the answer is yes, the program will stop. But in my machine, I'm using Go 116. So I'll switch here. So I'm on Go 116, right? If I go to halting, this is exactly the same code. We have a test function, setting go max procs, looping and triggering the function, sleep for 100 milliseconds, and then print done, right? If I run it here, it will be the same thing, right? It will exit. But I have another Go version in my machine, which is 1.13.15. And if I run the program with this, now the behavior is different. It prints start, and after that, it just gets stuck. Means it will not halt or it will not exit from the program. So the next question, of course, will be why different behaviors between different Golang version? And in order to answer that, let's revisit a little bit on Golang MPG model. So as we know, in Golang, we have a very powerful features called Go routines that enable us to do concurrencies very easily. But behind the scene, actually, the runtime does a heavy work of the scheduling. So in Golang, they model it as something called MPG model. The M stands for machine, or you can think of it as your OS CPUs, so how many CPUs that you have. The P stands for process, and you can think of it as a scheduling context, or some people call it a run queue. So basically, all your Go routines, which stands for G here, will be queued up behind a run queue, and its run queue will be assigned to a CPU in your operating system. So in this diagram, you can think of the machine has two CPUs, and we have two run queues. And for the first run queue, there are three Go routines. The first one is running, and the other two are being queued. And for the second run queue, there is one Go routine running and one Go routine is in the queue. When this Go routine, let's say, finish or context switch, it will be relinquishing the CPU, and the next Go routine can take up the CPU. And when the Go routine is ready, it can come back to the queue again, waiting for its turn. In traditional OS scheduling, we know that operating system can do preemption, right? It can force a process or a thread to relinquish CPU so that the CPU can be taken up by another process or threads. But in Go scheduler, in most cases, they are doing it in cooperative manner. It means that the Go scheduler, in most cases, will not force a running Go routine to release the CPU so another Go routine can run it. They are relying on something called checkpoint. So basically, there are codes in Golang that can signal the scheduler saying that, hey, you can do a context switching here, and another Go routine can take up the CPU. There is no exhaustive list in the Golang official documentation on these possible checkpoints. But if you look through online across the GitHub issues, documentations, or some tech talks, some people are listing the possible or the checkpoints that are already known. The first is by invoking runtime.GoSG explicitly. This will trigger your scheduler. And when your Go routine is doing syscall IO, of course, it is safe to do context switching. When you're calling a non-inline function, or to be precise, is when your stack grows. A little bit of extra information here. Another interesting part of Golang is each of the Go routine has its own stack, and the stack can grow, as opposed to the traditional stacks in OS threads, whereby the stack cannot grow, but the stack for Golang Go routines can grow because it is being managed internally by Go runtime. And the next one is when you're calling sleep. Of course, it's safe to do context switching. And when you're doing channel wait or mutex, it's also safe to do context switching. So coming back to our original code, as you can see, we are specifying Go max procs to 1. The Go max procs is actually changing the run queue. So no matter how many CPUs that I have in my machine, we only have one scheduling context. It means that at most, there is only one Go routine can run at any point of time. And when we sleep here, it forces the main program to relinquish the CPU, and the Go routine that we spawn here will take up the CPU. And because this is a tight loop and it just keeps on looping, it means there is no way for the Go runtime to context switch back to the main program. And this is the cause that this is the one that causes our main Go routine or main program is unable to exit. Once it finishes this line, it will never hit this because the only run queue that you have is being occupied forever by this Go routine. So this is a problem because if we have a tight loop, there is no possibilities for context switching to happen. And because of that, Go team has been trying to improve their scheduler, and they have added preemptive mechanisms in its Go version. And from if you use Go version 114 and above, you will not hit this issue because they are already able to preempt or force the context switching when it detects a tight loop. The GitHub issues is 10958. You can just look into it for the details if you're interested. As you can see, the issue is filed in 2015, but it is a long discussions, and it is going up to 2020. So it is a long process of improvement in Go runtime until the point that now they are able to preempt a tight loop. But you might say that, hey, this is a bug. Who will code this loop that will never finish? It is invalid. Yeah, you kind of have a point that this is an exaggeration just to kind of demonstrate what could go wrong with this runtime behavior. And in fact, if you look at this issue, I take this snippet from the issue itself. Someone proposed the easy way to reproduce the issue. In real life behavior, or in real life programs, what is more probable to happen is if you have a long running computations or heavy computation Go routines, you might delay your garbage collector, because in Golang, one of the stage of the garbage collectors requires stop the world, means it needs all the Go routines to go to sleep before it can perform the job. And if you have one Go routine that is long running doing computations and the Go runtime cannot preempt it to context switch, means all your Go routines cannot run because it's waiting for that one Go routine to go to sleep and then GC can run. So the more possible behavior that you can observe is your GC pause is longer than what it is supposed to be. And yeah, it comes to the conclusion that whenever possible, try to use the latest Go release, because in its release, there is a lot of improvements being added into the compiler itself that can improve the performance in one way or another. And a little bit of extra, we talk about Go max procs, which is by default being set by Go runtime to the number of CPUs that you have if you don't set it explicitly. But the question is, if we are in the environment like Kubernetes, whereby we can set a quota, right? So for example, if we set a CPU request to 1 and CPU limit to 2, and then the service is running on top of host with the CPU count of 6, what will be the Go max procs that is being set by the runtime? And the answer to this is 6, because for Go runtime, they are not aware of the quota that is being set by Kubernetes here via C groups. They're only aware of the CPU counts on the machine itself. In majority of the cases, this is fine for you to have one CPU and then 6 run queue trying to get the CPU, because the OS itself still can do time slicing for you. But there is an interesting repositories by Uber called AutoMaxProcs. It is basically saying automatically set Go max procs to match Linux container CPU quota. So if you look through the repositories, they are providing a benchmark to show that when you don't use the default Go max procs in environment that has CPU quota, you can have a better performance. Means that in this case, you should set your Go max procs to 1, and it might yield you better performance in some cases if performance is very critical to you. So I put a word consider. So consider to use this if your service is running in Kubernetes or any environments that utilizes C group or quota. All right. So yeah, that is the first one about CPUs and scheduling. Next, let's talk a little bit about memory. So again, let me explain a little bit about the program. We have a function called task alloc, which is just doing memory allocation of X megabytes. And then we are touching the memory in some of the bytes to make sure that it is dirty, so compiler cannot do any optimization on it. And in the main program, we are calling it 3 times, 100 megabytes, 200 megabytes, and 300 megabytes. Okay. And after that, we call GC explicitly to trigger the garbage collector, just so that we don't need to wait for the actual garbage collector to happen. And then we call a Go routine to print the memory statistics every 1 second, just to observe the memory behavior. And in the main program, we will sleep for 150 seconds, just to simulate a long-running process and to allow us to observe the memory behavior. So the question will be, what is the memory observed by this program? And again, the answer is it depends on your Go version, but this time it also depends on your operating system. The more interesting behavior will be on Linux operating system. So for that, I will switch to Linux VM. First, let me show you. This is exactly the same program. We have a task alloc function. We call it 3 times. We trigger a GC, and then we print the memory statistics every 1 second, and then we sleep for 150 seconds. Okay, and Let me clear the screen. To demonstrate the issue, I will use Go 113.15 again. Oh, just to brief you so you're not confused when I'm switching screen. I have a screen. Oh, sorry. Oops. Now I can't exit. Okay. I have a screen session called GoDoc, which I will use to run the program, and then my main screen I will use it to monitor the memory. All right. So I will go back to GoDoc. Let me run this. Okay. So as you see, because we trigger the GC, the heap in use is 0 megabytes. The heap release is 767 out of 767, which was requested. So technically, it should mean that our Go program is not holding much memory anymore, right? So let's switch back here. I run top. If you see, this is our main program. It's still holding 621 megabytes of RSS, which is kind of contradicting with what Go memory statistic reporting. If I switch back, oops, sorry. There is a screen on, there's no screen to resume. Okay, sorry, give me a minute. Let me just kill it. Okay. Sorry about that. Demo memory. Right, we are back here. Let me just run top first. Okay, there's nothing. So the question will be why the memory reported by Linux is different with what is being reported by Golang memory statistics. And to show you the difference, if I switch to doing this, from memory statistics of Golang, it is the same thing. It is saying that heap in use is 0, heap release 767 out of 767. Now, if I go back and I run top again, here is our main, but this time it is only occupying 20 megabytes, which makes more sense because the 600 megabytes that was requested has been released to operating system. So this is better monitoring results. So to answer that, it is because we can see the release note of Golang 116. Here it is saying that, give me a minute. Here. On Linux, the runtime now defaults to releasing memory to the operating system promptly using metfeed.neat, which is the one that we set explicitly with Go debug just now in Go 113, rather than lazily when the operating system is under memory pressure using metfeed free. So what happens is before or prior to 116, Golang default system call on Linux to release memory back is something called metfeed free. Metfeed free behaves in the way that a process release a memory back to operating system, but it says to operating system, hey, you can take it back if you want to. Means that operating system can choose not to reclaim back the memory. This happens when your system is not under memory pressures, because in some cases you want to keep the memory so that you can reuse it. By doing so, you don't need to make another syscall to request the memory in the future. This happens for Go 1 up to Go 115, whereby the operating system does not detect any memory pressure because we are the only service running there, so it does not reclaim back the memory. So that is why we still observe 600 megabytes in the RSS, because from operating system perspective, our service or our Golang program is still holding that 600 megabytes, whereby in fact, the 600 megabyte is free and can be reclaimed. And this happens that in production, you might observe that hey, my service is utilizing 2 GB and it never goes down. Where does the 2 GB go to? I mean, do we have a memory leak or some program is holding into it? And then you run a pprof and you see that there is nothing being held. The pprof shows nothing. That is because even for the pprof, it will not detect this memory chunk. Pprof is only reporting memory that is still alive, means it is still being used by your Go program. For memory that is being released but not reclaimed by operating system, it will not show on pprof. So it is double confusing now because the Linux say we use 2 GB, the pprof says that nothing is being used. This is because of this system call. And to avoid this confusion, Go runtime revert back to use metfee.need as the default, so that whatever that you release to memory will be promptly reclaimed back by operating system. Sorry, but if you want to still use metfee free, you can still use go debug metfee.need equals to 0. Then you will get back the metfee free behavior in Go 1.16 and above. All right. So again, it comes back to whenever possible, use the latest version of Go because it will help you to have the latest behavior, which is better in my opinion, and it will avoid the confusion in terms of monitoring on Linux. And avoid big memory allocation whenever possible because this is the one that might lead you to out of memory error and your process getting killed because the operating system is actually not reclaiming back your memory. And monitor your service resource usage. If it shows 2 GB all the time or even 8 GB all the time, something is wrong if you know that your service is not doing caching. So probably something else is happening behind the scene. All right. So yeah, that is a little bit about memory. So let's switch to the next one about race condition. Okay, sorry, give me a minute. We have a program here which is calling a reset function. So okay, I'll declare a global variable a and b. It's just that I omitted from the snippet. So reset will set a to 0 and b to 0. And f function will set the value of a to 3 and b to 4. G function will just print them out. In the main function, in the loop, every 200 milliseconds, we are calling reset and we are calling f to set the values in the coroutines, and we are printing them. Right? If we run them, 0, 0, 3, 4, 3, 4, 3, 4, kind of makes sense, right? Because it is either 0, 0 or 3, 4. Yeah, I'm trying to find the race condition, but since it's a race condition, it's not trivial to find. Yeah, you have to run it many times in order for you to hit it. Sometimes you might not even hit it. Let's run one more time. Okay, not that, but you can try it later, but I'll just show you why this is a race condition. If I go to race.1, right, so this is exactly the same code. You have AB, you're resetting it, setting it, printing it within the loop. Now, if I run it just as is, it's doing the same thing. Nothing happened. But if I add the flag race, it will call me that there is a data race. Read at main.go26, which is this guy, which is trying to print a variable, and previous write at main.go line 16, which is this, which is setting the value. So at a glance, it does not look like a race condition, but it is a race condition because in Golang, when you have multiple coroutines trying to manipulate or access the variables concurrently, there is no guarantee that they will observe the same order. This is, yeah, maybe easier for me to just open this. This is an official Go documentation. They call it Go memory model. Yeah, this sentence summarizes everything. If one Go routine executes A equals to 1, B equals to 2, another Go routine might observe the updated value of B before the updated value of A. This happens because the compiler can do reordering within a Go routine as long as at the end of that Go routine, it is still consistent. What it means is A equals to 3, B equals to 4 could be reordered by compiler in some scenarios into setting B first and then setting A. Because within this Go routine, setting A first or setting B first does not have any difference. It still leads to the same consistency as the end of the Go routine. Go runtime does not care that another Go routine is trying to access them, and it simply means that another Go routine could observe a different ordering. So that is why you should use the synchronization primitives like locking, or use the Go channel if you want to access and modify data concurrently across Go routines. And yeah, it leads us to the points that try to enable the race detector in your CI pipeline so you can detect race condition as early as possible and fix them. And some race condition might seem very subtle, and you might think that, hey, maybe this is not a race condition, but it is very unlikely for race detector in Go to be false positive. If Go race detector says it's a race condition, fix it. And bear in mind that the race flag only can trigger the race condition if that path of code is getting executed. So don't expect it to be able to do static analysis on your code and find a race condition in some function that is not getting covered in your test. So it also means that your test coverage must be big enough such that you're confident that most of your critical path has been covered. So you're confident that there is no race conditions happening there. Okay. All right. So let's move to the next one, which is actually not about runtime, but it is just interesting to me, so I added it to the talk. Probably from the title, you kind of can guess what is happening here. I'll briefly explain it. So basically, our program, this is a simplified and modified version of our actual code that hit this problem long time ago. I simplified it just to capture the gist of it. So we are trying to build some cache from some external service which supports some kind of pagination. So we need to pass like the page token to know that which page we are currently on. We start with an empty page token to signify that this is the first page to be requested. And for its request, it will return the results for that page and the next page token, an error. And for the results, we just populate it into cache. And if the return page token is empty, means there is no other page. If it is not empty, means there is a next page to be loaded. So we loop back and request next page again. And from this, you can see that the page token here, which is supposed to be the next page token, is the same variable with the page token here that we initialize on. So it is shadowing the page token here. So what happened is the page token in the next loop will be empty again, and we are back requesting to the first page. So if we have more than one page, we will get stuck forever requesting the first page because the page token will keep getting loaded back and use the page token value here. It leads to a very weird bug because you might start thinking that, hey, why my program never finishes? It keeps on getting stuck in this loop. What is happening? It can be easily avoided with linter. One of the good linter out there, folks, Golang is Golang CI lint. It supports a lot of linter, and specifically for shadow, you can use GoFet, but it is not enabled by default, as far as I understand. So you need to set the check shadowing to true for GoFet. And if we just run it, yeah, it will tell me that page token at line 17 is getting shadowed by line 19. So this is another good thing to be added to your continuous integration. Enable your linter so you can catch this kind of problem early before it becomes some weird behavior in your production. Okay, so yeah, enable linter and only allow nolin when comment is provided, because I know it is very tempting to just remove the linter for a particular function so that we don't need to fix the linter warning. But in most cases, it is good to fix your lint warnings as early as possible. Right? Last one. It is about finalizers. Finalizers is a very, I would say, interesting feature in Golang. In language like C++, we have a destructor, right? You can define a destructor for a particular object such that you can run some kind of logic when the object is getting destroyed. In Golang, we have something similar but kind of different called finalizers. Instead of defining something to be run when object is destroyed, you can define some logic to be run when an object is garbage collected. And because it is being run when it is being garbage collected, means it is not deterministic, because you can't tell when an object will be GC. Even when your object is already out of scope, your GC might happen sometime in the future, so you can't really tell when it will happen. One of the use case of finalizers is actually in the Golang source code itself, in the file unix.go. If you find for set finalizer, yeah. So for file descriptor, Golang is adding a final line of defense to avoid file descriptor leaks. So it's saying that when a file descriptor is garbage collected, means it is safe to close the file descriptor. And then because we already have this, then you might think that, hey, Go already settle it for me, means I don't need to close file descriptor, right? Then let's try it out. This is coming from this article, Tragedy of Finalizers. You can read through it if you're interested. Sorry. Basically, what it's doing is it is creating a temporary directory, right? And it just loops through 2,000 times. And for you to solve it, it will create some file. And at the end of the loop, the file descriptor for that particular file is no longer alive, means it will be GC. Then you might think that, okay, the finalizer will kick in and it will clean it up and it should be fine. But the problem is, if you're in Linux, so this is exactly the same program. We loop through 2,000 times, create a file, and not doing explicit close, right? And if I run it, it crashed because of too many open files. This is because, as we know, in Linux, we have a limit of the open files, which is default to 1024. And the thing with this finalizer is, because, as mentioned, it is not deterministic, it requires the GC to kick in. And because this loop is doing nothing, it runs so fast that there is no time for GC to kick in to clean up the files, and it hit the upper limit of the default Linux file descriptor limit. And yeah, so the take-home message is always call close or the equivalent, because we know in Golang you also need to close for example, IO read closers, and for sure for file descriptors. Call it explicitly to prevent leak. And the finalizer by itself is a cool feature, but there is a reason why it is under runtime package. Use it only if you know what you're doing and you're sure that this is the only way for you to achieve the behavior that you want. There are many discussions out there. If you look about finalizers, some people are debating that finalizer is good if you are designing, let's say, an external package. And let's say your external package demands the user to close something when it goes out of scope explicitly. So you want the users to immediately get notified if you forget to close an object, right? You can put a finalizers for the object and checks if during the GC time, the object was not closed explicitly by user, you can just fatal out. Your program will get killed and the user will immediately know that, hey, something is wrong. I used the external package wrongly. But of course, some people will say that, hey, it is not good to fatal out, it is not the right way, and so on and so forth. So some people are debating that finalizers is a good feature and can be used. Some people are saying that finalizers is not the way. And yeah, as it goes, it is a very tricky features, but it is there for you to consider if you really want to use it. And of course, in the context of Linux, try not to open too many files because we have a limit on it. But if your system really requires that many open files, then just remember to update your U limit so you don't hit the limitation. All right. I guess that is pretty much from me for today. And yeah, as mentioned, Acronis loves Golang, and we are actively hiring for Golang developers. If you're interested, feel free to scan the QR codes for particular positions that you're interested in, or you can just go to acronis.com/careers to find out more about the other positions. Yeah, I guess pretty much that's it for me. We'll hand back to Abel or Stanley.
We have
Thank
a
you.
couple of questions from Diraj, but maybe I'll share the question that has maybe some relation, but I think you answered it along the way. So he asked this during the GC when you mentioned object.
Mm-hmm.
So what he's asking, like, what do you mean by object? Does it mean variable?
Yeah, I mean, yeah, you can say because you assign an object or a variable. So what I'm saying is when the object goes out of scope, or yeah, you can say when the variable goes out of scope, then it will get GC.
Okay, so he had a follow-up question. So when you mentioned about memory leaks, if you don't close the objects, if you remember.
Huh?
Yeah.
Yeah, you can consider it as memory leak because at the end of the day, each object will need some memory to represent itself in a program. But in the case of file descriptors, it is also file descriptor leaks because as I show in Linux, there is a limit of how many open files. So if you don't close your files, it means for operating system, you're still holding to the file descriptor. So even though you actually don't use it anymore, the counter will just keeps going up. And if you hit the limit, then you will just get killed by the operating system. So it's also a file descriptor leak in this particular case.
Okay, so I think we'll go to the more general questions he had.
Mm-hmm.
So one of the does it fit? Okay, yeah.
I'm
So
learning to
maybe just
program in
general advice
Go.
on if you're starting on Go, right? What would you recommend someone to build or try out or?
Okay. Okay, maybe not specific to Go, but if you ask for suggestion, I would say that you can start by trying to find any like publicly available API and build something on top of it that might interest you. For example, if you're interested in games, you can find the publicly available API in games domains like, I don't know, like Dota statistics or some statistics, and you can build something interesting on top of it, like build some aggregates of statistics. You mentioned as a backend developer. Yeah, it's still applicable, right? Because you're calling API calls, it's still a backend. But yeah, you can visualize it nicely if you have some, front end programming too. Or you can always try to implement some nice algorithm of data structures back to the basic it is also interesting to implement those things in Golang and see how you can use Golang to solve algorithmic problems. Yes, follow up. What kind of topics or concept I must focus on? Okay. If you're asking explicitly for Golang, then I would say start with the Go tour, where Golang introduce all the key concepts. If you finish it, I think it's already a solid start for you, and you should be productive enough to build multiple stuff. And when you hit the issues, it will trigger you to explore more, and you will start finding articles, GitHub issues, Stack Overflow questions. Then for there, you will have the opportunities to learn a more advanced stuff. I hope it helps.
Okay, yeah, I think he said he thanks you for the answer. Yes.
You're welcome.
So we'll go to the next question from Saga. Since Go allows parallelism by using Go max procs, how do I know the right number of CPU cores we should assign to our application in order to provide the best performance?
Okay. If you're asking about performance question, the final, most people will say do the performance test, then you will figure out the answers. But in general, the default by Go is good enough, which is the Go max procs will equal to your number of CPUs, because it makes sense, right? If you have 8 CPUs, means at most you can run 8 Go routines in parallel at any point of time. But in some situation, if you run on top of some virtualizations like Kubernetes, you might have less number of CPUs than what is actually available in your host machine. Then that is why I show the Auto max procs, which can help you to automatically detect the right Go max procs depending on your quota that you set. Look through the repositories; they have a nice benchmarking on what is the relation if you have let's say X CPU, but you set your Go max procs as 2x, or if you set your Go max procs as X, and if you set your Go max procs as some value. So they have a nice chart that show you the effect of Go max procs with regards to your actual CPU. But in general sense, I would say in most cases, just go with the default by Golang, which is Go max procs equals to your number of CPUs in your host machine.